is by Peter Winterburn of MDRU. He's on the geochemical exploration for Skorpian-style oxide zinc deposits. That'll be interesting. Green's forward.
Good afternoon. I drew a truce with Dick before this meeting that I wouldn't ask him any questions about geochemistry. Thank you. If he didn't ask me any questions about this talk, so we're doing even so far. Okay, this talk is an interesting talk. It wanders off into the dim and distant past, so far back that some of you might not have been born. Yeah, there's a lot of great people around here, so I think a lot of you were probably born. I started some of the early work off, and then this was back in the days when I was with Anglo American. Then I hired John Barr to take over the geochemistry in Anglo American, and I cleared off to Chile to look at porphyries, which were much more exciting. And then Anglo American sold the project to Vedanta, which was very fortuitous for myself and John, because up to that moment Anglo American had sat on the Skorpion deposit and wouldn't allow anybody to do a great deal of presentations on it. When it got to Vedanta, they weren't particularly interested in sitting on the information anymore, and they were more than happy that we actually started talking about it. So this is a presentation that puts together a whole pile of history all the way through the exploration and some of the work that myself and John did on trying to see whether we could see this deposit, and you'll understand why we were trying very hard to see it. And then it goes on forward to look at the way that they actually developed their exploration geochemical technique, moving it forward, and then making use of new technology. It works. Okay, so here we are down in deep. Oops, wrong one. We've done it before.
The second one.
This one.
Dictates, yeah.
No. Okay. So that was the eject button. Here we are in darkest Namibia, at the bottom end of southern Africa.
Peter, this one works way better.
Yeah, no, this was just funny.
They're really expensive.
Oh, yeah, that's good. Good eyes out with this one.
Yeah,
Take down aeroplanes.
Be careful where you wave it.
So we're down in darkest Namibia. Back in the days when it wasn't Namibia, it was actually Southwest Africa, part of the South African Protectorate. And there was a zone sitting on the coast around a pier known as the Spergabite, which loosely translated as the Forbidden Zone, where nobody was allowed to go whatsoever. There was no human habitation, and people weren't allowed to go into it. And the reason for that was that there was diamonds mined all the way up the coast here, and somebody had calculated that it was impossible for somebody to walk with a pocket full of diamonds from the coast all the way through here to the nearest road. And that was a fairly simple principle. It was about a 2-day walk, and it's all hot desert. In the mid-1970s, the laws started to change because they realized that they had potential for exploration here. Anglo American were very lucky because they were in cahoots with De Beers at the time, and they essentially had first dibs on doing exploration in this area. Not surprisingly, this particular area we're in was a potential area of great interest, because sitting down here we had the Roche Pinard zinc mine, which is one of those mines that keeps going on and on and on and on. It permanently has a 5-year mine life, permanently, and has been going there for, must be around 60, 70 years now, so this 5-year mine life. And obviously this old zone sitting at the side here was of potential interest to find more VMS style deposits. So Anglo American set about a exploration project using stream sediments to see whether they could find, see if they could find more VMSs. So we drop into the exploration history. In 1976, Anglo American targeting VMS style mineralization. They picked up a stream sediment anomaly running a 115 parts per million zinc. And that's an awfully low number for an anomaly, but they're sitting there with zinc against a background of 30 to 35 parts per million, so it's fairly significant. And it wasn't very long after they started following up that anomaly that they stumbled across this material down the bottom there. There's a lead, zinc, silver, barium, gossen, so they found exactly the right type of rocks that they wanted to find. Whereabouts to set upon some fairly simple geophysics and started deep drilling for VMS. Everything was looking really nice and fairly simple at that point. The funny thing was that they didn't actually find what they wanted. I've actually jumped to the next slide before I should have. Spoiling my own presentation now. They were back in the days of doing reasonably good sensible geology. They were drilling down through something like 800 meters of a fairly unexciting looking rock to hit this VMS deposit, and they were hitting the VMS deposit exactly where they were supposed to hit it. And being sensible geologists, all they were doing was picking out the sections that were containing sulfides and sending those in for chemical analysis. The rest of the material, which was this awfully bland, unexciting looking rock above the VMS, all of that was just going into the core shed. One day, a geologist who nearly lost his job, he accidentally carved up and sent in a whole 800 meter plus string of core in for chemical analysis, which didn't make his manager particularly excited. However, when the results came back, everybody got phenomenally excited, because sitting in this 800 meter string, they suddenly found phenomenal zinc values. The zinc was actually going up to 20 meter intervals running at 54% zinc, which was the theoretical maxima you can get in the mineral that they were hitting there, which was Skorpion, which is a zinc clay. Not surprisingly, all the rest of the core got dragged out at that point. That's what the core looks like, and it's very uninspiring. It doesn't get anybody excited. You look at that, there's nothing shiny in it, nothing shiny that's going to get management excited. One of the great things about zinc-oxide minerals, which is what was sitting in here, is that you can do very simple chemical tests to identify them in the field. And this beautiful chemical known as Zinc Zap, which is a mixture of acids and potassium ferricyanide. And you mix this mixture together, you paint it onto the core, and in the presence of zinc, it goes bright red. And it wasn't long before all the core was being painted as quick as it was coming out of the ground with Zinc Zap, and being sent in for chemical analysis. So they found a zinc oxide deposit, which was the last thing they were actually looking for, but it was very nice to find a deposit, full stop. But it was much higher grade than the zinc they were going to get out of the VMS. They did a considerable amount of drilling, and it wasn't long before they'd pulled out a resource of 8.3 million tonnes running at just short of 11% zinc as oxides. The problem was that this was a zinc oxide dominantly sitting in clay as a sorconite, and they couldn't get the zinc out of it. They tried doing the obvious thing, which was to do a sulfuric acid digestion with a lead forward to electrowinning. The problem was that once it got into the acid, the stuff would form a disgusting gel from which they couldn't actually extract the zinc effectively. The silicate was forming this horrible gunk. And so Anglo-American sold 50% in a share of this deposit to Reunion Mining. It was a fairly small company at the time, back in 1996. As you can see, they'd sat on this now for 20 years trying to solve things. So they sold it to Reunion Mining for a mere $5 million, 50% of it. Reunion Mining did considerably more drilling. They proved it up to 17.5, but just under 10.5% zinc. And they stumbled across a little-known mine sitting in Spain, where they'd actually had exactly the same problem, and they resolved the metallurgical issues. To actually go and see the metallurgical plant is quite fascinating, because they have a continuous filter process where the sludge, as it is, rolls out along a conveyor belt, that's a filter conveyor belt, and they're actually continuously spraying it with sulfuric acid to keep the leaching going while this material is moving forward. And then right at the end of the conveyor belt, they effectively press the material to squeeze the last remains of sulfuric acid, zinc out of the cake along with the sulfuric acid. Well, having solved the metallurgical problems, Anglo-American then bought back into it. They paid $50 million to buy Reunion Mining. They just took the company off the market altogether. That was a pretty good profit margin for Reunion Mining. Over 3 years, 5 million became 50 million, which isn't too bad. Anglo-Americans set about a feasibility study, and in 2002 they started mining the deposit with a $454 million investment. And when they started mining, essentially they'd upgraded the thing even further to 24.6 million tons, running at 10.6% zinc. Even at that point, they were still nervous about the metallurgical process, to the extent that they built a laboratory scale pilot plant, and when that was working fine, they then built a pilot plant at their research laboratory in South Africa. When that was fine, they then built up a small scale metallurgical plant out at the actual Skorpion site, and when that was working fine, then they finally built the large scale metallurgical plant. They were very nervous. There was a lot of money in those days. They finally built this large-scale metallurgical plant, and things worked well, mostly from that point onwards. The great thing about the product, as we'll see later on, was that during the process of the formation of this deposit, a lot of the nasty trace elements that often end up going through to zinc electrodes never got into the deposit in the first place. And so the material they was producing was super high-grade, ultra-pure, mega worth a lot more money zinc, which was earning prime dollar when they sold it on the open market. So it was a very good investment, for them. And then in 2010 or thereabouts, Anglo-American decided to divest out of zinc. They sold off all of their zinc operations. Vedanta Resources took over Skorpion, and the last number I saw, which I took off their website last year, was that they're sitting with about 11.4 million tons at 9.5% zinc as oxides. And the metallurgical plant is still working the way it was designed. And this is a brief look at the geology of the deposit. This effectively is where the VMS would have been sitting, and most of that VMS is now gone. The sulfides are sitting right down the bottom here. And sitting over the side here, we now have the zinc-oxide deposit, where it's mostly a mixture of sulfonite and various zinc carbonates. Mineralization essentially worked its way from the VMS lenses as sulfuric acid mix, essentially, ate its way across and was being precipitated out in P-lights against this carbonate front. And all you're actually doing was replacing the clay minerals with the silicate minerals with a zinc clay. Very simple. And you can see these large faults were forming conduits, and then the actual contact between these two units was forming a fairly obvious conduit, because this carbonate here would be a killer for any sort of chemical reaction. As the fluid migrated across, a lot of the other elements that we wouldn't like, things like copper and manganese and lead, they never actually got over as far as here, and there are zones sitting out here which contain lower grade zinc resource, but they contain much higher copper and lead contents, and those ones they've left in the ground. They haven't touched that because it's not suitable to put through the plant, as it would reduce the value of the final product that they actually sell. That's just brief geology history out of Katrina Kerner's thesis, so we did a whole pile of work on here. Essentially, the deposit itself was formed a long time ago. It was unearthed about 65 million years ago, when this area was a lot wetter than it is now. It was a subtropical climate, and not surprisingly, stick a VMS in a subtropical climate and it's going to oxidize at a fairly phenomenal rate. Conditions changed to semi-arid, and they believe that's where the deposit started to actually form. And then the whole thing was buried somewhere around 40 million years ago. It actually sits on the bottom of a valley. I mean, it's fairly soft material, so it's fairly easy to weather and remove again once it's converted to the oxide. And this was being stripped off, so it sits in a valley, and that valley around 40 million years ago was infilled with a whole pile of gravels and clays, which is where we got involved. As I said, a whole pile of strange minerals. Some of these people have heard of, some of these people won't have heard of, and the special mineral there that actually derives its name from the operation is scorpionite, which is something not many people have in their collections. And if we go back to the geology, one of the things you'll notice across the top here is this awful little grey area, which it's interesting to call it grey area, little grey area that most of us wouldn't go anywhere near. And that is the material that makes life very difficult, and which is why nobody else had ever found this oxide deposit, and indeed probably why the oxide deposit has been largely preserved. And that is because it's buried under 20 to 30 meters of mixed alluvium and colluvial gravels, with various layers of carbonate in between. There's a silkcrete sitting down the bottom here, so it tells us about some mobilization elements through water, and then various layers of calcrete, essentially breaks in the sequence as the actual gravels were being laid down. The problem came up, of course, of having found one, how are we going to find the next one? Because one was, great to go and build a plant, but a plant's a lot of money. Is there going to be more ore to feed into this plant when this particular deposit runs out? Well, we already know that classic residual geochemistry isn't going to work because the deposit's buried. We're not going to see it using classical chemistry. We tried using regional outcrop lithology, but the scale on which we could apply it was actually far too wide, and obviously there's only going to be sufficient outcrop once you get into the mountains, which is not where we're expecting to find one of these deposits. They tried geophysics. They threw every possible geophysical technique that they could think of under the sun at it. And this was one of the very strange things that they did. I think they spent about $2 million on geophysics in the end, flying all possible machines that they could. There was no groundwork done beforehand, quite interestingly, on physical properties. And even though 2 metallurgical pits had been dug into the ore by this time, nobody took any samples from the metallurgical pits to see whether there was actually any sort of density contrast. And we all can't expect, anybody who expects to get an EM response out of a zinc sorconite is being very hopeful altogether. They could obviously see the VMS, that the money being thrown at the oxide was trying to see something that they weren't going to see. It's also no longer wet. It's well below the water, well above the water table. So even soaking the clays with water wasn't going to help them a great deal. They also tried hyperspectral. Again, they flew their own plane across the target to produce across the whole region actually to produce a gigantic map. And this was back in the days when we had 20, 40 kilobyte hard drives, and they were struggling to actually process the information because you couldn't get it all on one hard drive to actually crunch. And that was a very interesting thing. I sat there one day with the hyperspectral geologist, and they were sitting with all the data, and he was telling me that they were really struggling to get very much out of this. Because nobody got any idea what the hyperspectral spectrum or the shortwave spectrum, infrared spectrum of sorconite was supposed to look like. Again, basic groundwork to actually identify what they were looking for wasn't actually carried out. The interesting thing that again they actually did have a source of material, and indeed that material was sitting within the hyperspectral image, because the two pits that they'd sunk to take metallurgical sampling, some of that material was actually being dumped on top of the pits containing the ore grade, or on top of the spall tips containing the ore grade material. So that left us with little else to try but good old geochemistry through cover. Could we actually see the deposit through the transported overburden? Along came 2000, and I disappeared out to Skorpion with a couple of likely lads from a local village to start digging holes in the ground to see whether we could produce a geochemical response. When I arrived in the field, this is exactly what it looked like. This was a photograph I took on a day looking down one of the sample lines. This is back in the days of pre-digital, so those with good eyesight can see the join down the middle. Here sits one of the metallurgical holes they dug into the gravels to get down to the actual deposit, and there sitting at the back is a spoil heap with some of the ore material on, and then just behind me, where I would have been taking this photograph, there sits another hole as well. Now, it was pretty novel at the time for Anglo-American to actually take two bulk metallurgical samples, because most metallurgical test work in those days was only ever done on one sample. You can see one of the problems immediately that came up was that there are at least 6 drill rigs sitting in this picture, and they're a mixture of RC rigs and diamond rigs. And RC rigs, as we all know, are notorious for spilling crap all over the surface. Dust blows everywhere. Here we are out in the wide open desert. What's happening to all that dust that they're digging out of the ground when they're drilling these holes? Well, we had a plan to try and get around that. We went out there, we put in 4 sample lines, took in a whole variety of different samples. A shallow one at 30 centimeters, which was your classic geochemical sample in those days. A deep sample, which we would dig all the way down until we hit the top of the calcrete layer, or the deepest we went to was 1 meter if we didn't intersect calcrete. And then we also sampled some of the calcrete, which was to see whether any of that anomalous metals that had actually been caught up in the calcrete itself. And as always happens when you do a survey like this, we actually got a geochemical response, and we got one in exactly the right place. This is actually the deep sample, not the shallow sample, and this is used in AR-ICP-MS back in the early days of such techniques on the 180 micron sample. There's the actual ore body. This is the 1% zinc sub-outcrop of the mineralization, and here we have a very nice anomaly popping up across the top of the deposit. This dot here is actually anomalous in a whole pile of other elements that aren't sitting in this ore body, and that's actually coming from the gossan that sits further off the picture that has spilled down. So we could discount some of the anomalies on the basis of the chemistry they actually showed as being brought in from the weathering gossan. Well, by 2001, they'd actually started stripping the overburden off the ore, and that gave myself and John Barr. This is John Barr. Those who know John Barr know this is a very slim John Barr. We embarked upon sampling. It was great to do this sampling because using modern health and safety requirements, we would never be allowed to do this again. But we propped up ladders along the side of the pit wall, and we went in with plastic bags, essentially dug out, I think it was 1 meter trenches, and screened that material to throw away the pebbles and just keep the superfine material. At the same time, there was an old Anglo-American pit here where they, in the early days, had tried to find the mineralization. It's only about 1.5 meters deep, and they realized it wasn't going to be that close to the surface. But the great thing about it was that there was a rubble layer, which was where they'd hit the calcrete when they'd been digging their hole, and then all the sand pointed up on the top of that, which had blown across, so we could actually identify the point at which had been pre-mining. So pre-drilling. So we could look at that to see whether we could clearly define contamination in the surface. This was looking at those data from that pit, and very clearly you can see that it is a 30-year rubble line. So that rubble line there is 30 years old, so it predates most of the drilling. All of this material has accumulated on the top of that rubble line since it was actually put there 30 years ago, and we had a fairly strong anomaly sitting inside there of a whole pile of elements. I mean, we've got zinc here going up to 700 ppm, and very few people in their right mind would ever envisage that we're going to mobilize 700 parts per million zinc up from a buried deposit. This type of material was clearly contamination that was being brought in from that 30 years worth of drilling that's happened over the target. So we look at some of these profiles from the pit walls that we undertook, and the geochemistry that came out of those was really quite fascinating. Even looking at those elements that normally wouldn't get us excited. You see the calcium nicely leaps out where the calcrete is. We look at many other elements. We can see nice dropbacks as we go into the modern sands and the calcrete, showing the dilution of the composition of those gravels. And then things started to get exciting because we saw some of this data, and you can see we've got kicks sitting immediately below where the calcrete was, and that gave us the feeling that, well, perhaps something has happened. Perhaps there has been mobilization of the trace elements, and obviously a lot of that trace metal is going to hit the calcrete, and there we're going into a phenomenally alkaline environment, and it's not going to be mobile anymore. It's going to be mobilized and dropped out. What got the geologists on site much more excited, however, was the fact that just at the interface with the bedrock, and they were also getting elevated concentrations of a whole pile of interesting elements at fairly elevated levels. That took them then back in 2003 to the idea of, well, perhaps we can use a cheap technique such as RAB drilling to see if we can identify mineralization at the unconformity surface. Mineralization had obviously been mobilized, as I said, there's a siltcrete there where water has dropped out a whole variety of dissolved components. The potential was that groundwater had also taken some of the chemistry out of the oxide ore body, and likewise moved that along that unconformity interface. One of the things I always find funny is, and many of the older people here go through the same thing about how we reinvent the wheel. And if you wander down to Australia, they're all getting excited about this new concept of unconformity sampling. Unconformity sampling is nothing particularly new. People have been trying it for a long time. It's a new technology. So yes, that idea came up. Can we do drilling to identify the unconformity, the anomaly of the unconformity? Obviously, if you're going to drop a drill hole down to the unconformity, you're not going to stop there. You're going to carry it on into the top of the bedrock as well to see what's in the bedrock. So Anglo-American embarked upon this huge RAB drilling program, phenomenally cheap drilling type of technique. You're just drilling through unconsolidated sands and gravels, so it's fairly easy to actually cut through. And this was a typical type of profile that they put together when they were doing the pre-survey orientation to see what chemistry was coming out. And you can see there are the bedrock interface. This is a 2-meter interval. You've got a whole kick in a whole pile of interesting elements that we would hope to see. From that, John Barr by then was working on this, and I was out of it. He put together what was known as the Skorpion Index, which was little more than accumulation of a variety of elements that were anomalous relative to the gravel background. They applied that to both the base of the gravel as well as the first intersect of the bedrock. And there was obviously some complexity here because some of these elements we know are going to get beautifully absorbed into manganese, so they actually normalized some of them against manganese to take out that concentration effect that manganese has on some of these elements. We come to modern times, and suddenly we have routine field portable XRF technology available to us. And so what became of the old exercise then was no longer the samples being submitted to a laboratory, and they would do their RAB drilling. They would drill down to the bedrock, and they would drill down to through the top of the bedrock, and they would screen all of the samples for the last couple of meters samples for a whole pile of elements using the field portable XRF. Those samples that returned values that were much greater than the background in a whole range of elements, those that conformed to the Skorpion Index, they would then get sent into the laboratory for further analysis to try and define the anomalous response. Fairly simple idea, fairly simple technique, making use of modern technology to speed up the process and maximize the exercise. In addition to that, there's obviously a great deal of other information you can get from the RAB drilling. From the RAB drilling, you could define the overburden thickness and the pre-overburden paleo surface. So there we had 3 different surfaces: the current and the paleo surface, as well as the thickness. That allowed them to actually understand what their anomalies meant, because obviously you're expecting dispersion to go downhill. I think there's a whole pile of sections of slides here. That took them on to what became their standard exploration technique, which was to do this large-scale RAB drilling program. They would bring in the Palaeo-topographic surface to model. They would develop that from the RAB drilling to model exactly what was happening underneath in terms of the pre-gravel fill land surface. By drilling into the first couple of meters of the bedrock, they could obviously put together the sub-outcrop geology, and then put together their Skorpion Index in terms of those samples that were sent in for multi-element analysis to define anomalous responses. And from those, that's the bedrock, and the previous one was the deep gravels. And from that, put together things like target selection maps to pick out targets that they would follow up on. Of those targets, only this one is so far yet proven to be of a great deal of value. And unfortunately, that one actually isn't a secondary oxide deposit. It's actually another VMS deposit, and they're picking up the dispersion of that. It's great to find another deposit, but the downside is that Vedanta, who now own this, they can't move that material into their current plant. It's only expecting oxide zinc. So if that one goes ahead as an operation, the obvious thing to do there is to sell the ore off to Roche Pinot that sits down the road. The great thing about having all the Palaeo-topography was that you could do sensible interpretation of the data, so that, for example, you can see the deposits sitting up here. We've got some large-scale drainage coming all the way down here that would actually run off of where the Skorpion deposit would have been when it was subcropping, and not surprisingly you see a whole pile of value sitting all the way down here that are essentially Palaeo-stream sediments sitting in the base of this base of the valley that are derived from the weathering of the deposits. That knowledge is particularly useful because it stops you from picking out a whole pile of targets that are nothing more than transported anomalies. So then we go back to the question of did we see a response in 2000? They've done their work. Nobody believed that the geochemical response we got actually meant anything because they were concerned about all these drill rigs that were spewing material all over the surface. So surface geochemistry actually stopped at that point. There were potential ways by which geochemistry could have got to the surface. The calcrete was obviously formed by the movement of groundwater up to the surface where it was precipitating out. And there are in fact insect nests going down all the way into the ore material itself as the termites chase the depleting or the disappearing groundwater as it sunk down below the ground surface. So termites could well have brought material up to the surface. And then there are faults that have been reactivated that now cut through the gravels. So the same way that we all like the idea of seismic pumping for bringing chemistry up to the surface in Chile, the same thing could have happened here with groundwater bringing up some of the chemical signature. However, of course, we still have the active windblown sand surface that would have diluted a great deal of that chemistry with nothing more than essentially pure nibbling silicate. If we look at one of those profiles, this is now the actual shallow profile. You can see we've got a much broader anomaly there than what we saw earlier on. There's the peak anomaly that we saw just using the the deep sample, the 1 meter deep sample using AR-ICP-MS. And then using a whole pile of other techniques, we actually also respond that same anomaly. Now these techniques aren't supposed to be picking out any of the material that's dropped on the top. They're supposed to be designed to pick out nothing more than ions bound to various other media that have been transported there nefariously, as I like to put it. Those, still not convinced about those. However, here we sit with the calcrete. And we actually took the calcrete, myself and John, and we sat there the one day, we hammered this calcrete to pieces and selectively pulled out inner core chips from the calcrete material. So we weren't then worried about any contamination that maybe washed down through the sands and ended up on the outsides of the grains. And on those calcrete cores, we get the same geochemical anomaly in exactly the same place, sitting at 200 parts per million zinc, which is a pretty convincing anomalous response. So we feel that we actually did see something, and the potential was there to use surface geochemistry as an exploration technique. However, that was superseded, and I think quite rightly so, by a much cleverer technique of using what was a very cheap drill technique to essentially rab the area to death and do the unconformity sampling and the first hit of the rock. The great thing about that type of technique is that you also sterilize the area. You don't walk away with that feeling of, well, perhaps we've got a false negative and there is something there. With that type of RAB drilling, you're not going to miss anything. Unfortunately, we can't go back and do any further work in this area to see this would be a fantastic test site, but the potential as a test site has completely been blown now. The samples now sit where there is a rather large pit and a metallurgical plant. So that opportunity has been taken away. I don't think the samples exist anymore either that we originally collected. One of the other great things about Skorpion is that the mine is full of a whole pile of very esoteric minerals that fluoresce. And so not only were the people painting the stuff with Zinc Zap, but they could also go down the core looking for the various carbonate minerals that fluoresce. And likewise, they could go down the pit and actually shine the UV torches on the pit walls at night to try and see where the mineralization was and where it was actually going. The downside of ultraviolet light is it also makes scorpions themselves fluoresce, which is not a great thing to be going to stick your hand in to pick up if you think you found some interesting zinc minerals. Thank you.
Just a comment. The Skorpion deposit is really highly unusual in terms of its relationship with the host rock. Because I guess in the bedrock, there's carbon in the calcrete, but in the bedrock there's almost no carbon.
In the bedrock, there are
Can you
some
repeat
limestone.
that?
Pardon?
Couldn't hear you, Charles.
I said that the Skorpion deposit in the bedrock, there's very little carbon, which really is the key that allows them to actually use a sulfuric acid process, because most of what we call the oxide zinc deposits in the world are hosted by carbonate, and it makes them unsuitable, really, generally speaking, for this type of process. So it's because it's really a VMS deposit, right? It's been weathered and dried out, and now it's clay, zinc-rich clay.
Anyone want a translation? There obviously was carbonate there. You can see there's a huge pile of carbonate, and in fact there was a very clever geologist who was working there with reunion mining, who once he got the hang of the idea that sulfuric acid was going to be a potential digestant, and realised that somewhere along the line they were going to need a lot of neutralising capacity to clean up sludge and other such things. And he actually went out and pegged all the limestone outcrops in the immediate vicinity, so that if they wanted limestone, they were going to have to buy it off of him.
Well, I met John Barr at the Anglo booth, and I believe he's the longest serving Anglo employee still with them. And I think this story would not have been possible without that sort of racial memory going back to the company. I mean, you just imagine the sort of work Peter was describing, if there were the typical 5 to 6 companies that handballed this one to another, there would have been no continuity of concepts and what had gone before. It's unfortunate. I don't know what sort of documentation sits inside Anglo, but I expect 90% of it's inside John's head. Which is, you disagree or say?
No, I completely agree. Now, most of the people that worked on this deposit, people like Roy Corrins, they're out of the business now. They perhaps have their own independent companies. But a lot of that knowledge of certainly the dark history of the past is disappearing, and certainly a lot of the research is sits in small memorandums, notes of the record that disappear into the archives.
Yeah. Well, I mean, capturing this one was I think particularly fun because it shows that companies can keep the information together, but I know the one I used to work for, I mean, they spent gazillions on getting databases together, and they could barely find what they did last year. It's not very good. So anyways, there's hope on the deposit. It's a very rare one, maybe some more, but we're going to take a short break and we'll get back. So thanks very much. And the coffee and I think some cookies are outside.